We're now going to examine the tension force with two blocks. Here's a 20 kilogram block and a 50 kilogram block attached by a massless frictionless string on a frictionless pulley. This was first used in 1784 by George Atwood to demonstrate the constant acceleration of such a system. Because we are assuming a perfect rope or string, the tension on both sides will be the same. If it were not, then the rope would stretch or it would compress, and that would add a lot of complexity to the problem. So we'll just assume that the tension is the same. Here's the problem that we'll be addressing. Problem 3, tension force. A 20 kilogram mass hangs from one end of a rope that passes over a small frictionless pulley. A 50 kilogram weight, over here, is suspended from the other end of the rope. First of all, let's determine which way will the 20 kilogram mass accelerate and the 50 kilogram mass. This one you can actually use your intuition and common sense. This is a much larger mass than here, so if we have these on a pulley, this weight will be pulling down. This weight is also being pulled down by gravity, but the force of gravity is greater on the 50 kilogram mass, so what will happen is this will rotate in a clockwise direction. So to solve this problem, we'll start by drawing a free body diagram for each mass. We will then use Newton's laws to write the net force equation for each mass. This will enable us to find the tension force, which as said previously is the same on both sides. We will then find the equation for the acceleration, find the acceleration, and then finally find the value of the tension force. So here are the free body diagrams for each mass. The 20 kilogram mass, as we just discussed, is going to go up as this entire system is rotating clockwise. So we draw the acceleration vector in the upward direction. Here's the gravitational force, here's the tension force. On the 50 kilogram box, that's going in a downward direction, so here's the acceleration. It's being pulled down by gravity, and it's being pulled up by the tension force. Now notice once again the tension is the same for both masses. However, the direction of the acceleration is different. How about the magnitude of acceleration? You would expect it to be the same, because if the rope is not stretching or compressing, every piece of the rope must be moving with the same acceleration, the same velocity. So later on we're going to find that the acceleration is absolutely the same for both. The next step is to write the net force equation for each mass. Now remember, there is no special equation for tension. We need to use the net force to find the tension. So at your desks, below each diagram on your piece of paper, write the net force equation for each mass. Now note this positive and minus here. We always take positive for all our forces to be the direction that the object is accelerating. So over here, since the object is moving up, positive is in the up direction. For the 50 kilogram mass, the acceleration is down, so we will take down as the positive direction of acceleration, and also any forces that we look to resolve here. So please take a couple of minutes now and write the net force equations, paying careful attention to the signs. Write the net force equation for each mass. We'll start here with mass 1, and we'll note that the tension force is up, gravity is down, so we will sum the forces according to Newton's second law. They will equal m1 times a. Tension gets a positive value right here because it's heading up, and m1g will be negative because it's pointing down. You sum them and you get m1a. For the second mass, the 50 kilogram mass, we have the tension is going up. However, this time the up direction is negative. So that will be negative F sub t plus m2g, which is heading down, equals m2a. So the question at the bottom, what do you notice about how the signs were chosen for the various forces? Just think about that for a minute. If the force is in the direction of the acceleration, it will be positive. If the force is opposite the direction of the acceleration, it will be negative. Find the equations for the tension force F sub t. We now have two equations, one for each mass and two unknowns, tension and acceleration. This means we can combine these equations because we're now dealing with simultaneous equations that both have to be true. So two variables, two equations, we're in business. We take the first one for mass 1 and we just solve for Ft. In this case, all we have to do is put m1g on the right side. So we have the tension is m1g plus m1a. For the second mass, m2, we take it right down here and we do a little tiny bit of algebra and we find that the tension is m2g minus m2a. So I have this equation here is equal to the tension. So is this. So since they're both equal to the tension, I set them equal to each other. And then at the bottom we have m1g plus m1a equals m2g minus m2a. We are now ready to find the equation for the acceleration. We have the two tension equations here from the previous slide that we set equal to each other. So we want to solve this equation for A. We will add m2a and subtract m1g from both sides. So as you can see, we've now isolated the acceleration on the left side and we've got the g on the right side. We factor out an a, so we have a times m1 plus m2 is equal to m2g minus m1g. Our last step is to divide by m1 plus m2, and here we go. This is the equation for the acceleration. Now that we have the equation for the acceleration and we have the given values, it is time to substitute and solve. And remember, this acceleration that we're finding will be the acceleration for both objects as they are connected by a string or a rope that is not stretching or compressing. So let's pull out the answer box. Here's the equation we had on the previous page. We substitute the values in for m2, for g, and for m1. Do a little math, and we come up with the acceleration of the system is 4.2 meters per second squared. And remember, the 50 kilogram weight is going down with that acceleration, and the 20 kilogram weight is going up with that exact same acceleration. The problem is now ready to be finished. Find the value of the tension. We have two equations for tension, and since they both must be true, we can actually use either one, and they should give the same answer. So let's look at them. We have, this is the tension for block 1, m1a plus m1g. We plug in the values, and we get the tension force is 280 newtons. Then for the second block, we do the same thing, slightly different equation, substitute in the values, and we get 280 newtons, which shouldn't be surprising because this is what we expected all along. The string is not stretching, it maintains the same exact tension. So the tension is the same in both ropes.